In fact, you may not be able to tell whether you are dealing with a guy like this or with a native Chinese speaker. So this whole system is going to pass the Turing test. But does this guy understand any Chinese? This guy does not understand a word of Chinese. He's made no progress at all in an understanding of Chinese. So you have here something that is, in effect, a computer doing everything that an artificial intelligence program could do. Everything that the artificial intelligence program could do is written down in the book. So he's completely simulating the computer. But he doesn't understand anything of what's going on. So if a computer was doing that stuff, it could be doing it all without understanding any Chinese at all. If your brain was doing all that stuff, it could be doing it without you understanding any Chinese at all. So this just can't be what understanding a language involves. The whole computer of the model of the mind is a mistake. The whole AI project is a mistake. The whole of psychology is founded on a mistake. There's no way you could learn any Chinese simply by manipulating these formal symbols. A computer has a syntax. That is, it can recognize the shapes, the physical shapes of the signs it's dealing with, and operate them with accordingly. But no semantics. That's to say, it doesn't know what any of those signs stand for. It doesn't know what would make them true or false. That's the Chinese room objection. Let me put this another way. Let's suppose you've got a calculator. Calculators? You get? In the old days, there used to be calculators, but you get calculators on phones, right? You want to do a sum? Okay. So suppose you've got a suppose you've got a calculator that can do hard sums, and you say, how is it doing that? Suppose you've got a calculator that can do multiplication, and you say, how does it do the multiplication? Well, how might it do the multiplication? Who? Louder? By addition. Very good. Who said that? Okay, very good. Yeah. How can you do multiplication by addition? Isn't that just a mistake?
So you put in 12 times 3.
Yeah.
12 plus 12.
Very good. Okay, I have here one I prepared earlier. So here's a flow chart for how you do multiplication. I suppose you want to multiply, you said 12 by 12. Okay, that's pretty big. So suppose 12 by 3. Okay, let's multiply 12 by 3. 12 by 3. Okay, so I'm trying to find out what the answer is. So over at the left it says, let's make A 0. So let's make A 0. And then we move over here and we say, is N 0? Well, what's N? N is 3, right? So is that 0? No. So if it's not 0, then you subtract 1 from N. So that's 2. And then you add M to A. So M is 12, so I add 12 to A, which is 12 plus 0, which is 12. And then I go back to the start. Oh, let's see. No, wait a minute. Where am I? I go back and I say, is N 0? And I say, no, N is 2. So I subtract 1 from N, and I add 12 to 12, which is 24. I am not a machine. Here we see the superiority of the human to the machine intelligence. 24. Okay. Is N 0? No, N is 1. So I subtract 1 from N, which is 0, and I add 12 to 24, which is 36. And then I say, well, is N 0? Hey, N is 0. So I stop. Hey, look at that. Okay. We just multiplied 12 by 3. Okay, and as you say, we did it by adding. right? Okay, so that's a computer. Right? A mere machine could do that a bit better, actually. But that's the kind of stuff a computer is doing. That is the formal manipulation with symbols. But now suppose you ask, well, how is it doing the adding? Characteristically, you might get some answer like, well, it does the adding by reducing everything to binary. And then you say, well, how does it do calculations in binary? How do you make a machine that does calculations in binary? Well, what we did here was we took a complex computation and bust it down into simpler computations. But with binary, when you've got an AND gate here, and you've got an OR gate there, an exclusive OR gate there, how do they work? How does the computer do the adding in binary? Okay, you guys gave an answer for the multiplication here. What's the answer here for the binary? How would you do that? How would you bust that down? You can bust down multiplying to adding. How can you bust down adding in binary? Yep?
Like, if you have in the first column, you have a 0 to 1, then you carry down to 1. You have 1 and a 1, then you carry over to 1. And you have 0 and 0, and this is 0. And then it just keeps doing that perfectly.
That's right. That's exactly what the system is doing. Right? You just described what the system does. Yeah? But I'm asking you a question that might not seem quite intelligible. Namely, how is that done? Multiplication here got broken down into addition. Right? I said, okay, here we've got binary addition. How do you break that down? And my general point is you can't break that down. This is where it comes to a stop. Because all you've got here are switching circuits. Here you've just got electricity. That's what's so good about binary, that you just got switches that go on or off, on for a 1, off for a 0. Yeah, that's all you need. So wherever you have complex operations, like multiplication, and you say, oh, well, I've got a computer doing this, you've got to, in the end, come down to primitive processors, where they're just doing, they're just realizing the thing without breaking it down into any more primitive computations. If you want to make a gadget that does this, you just need to move to electricity. You just need to make some switches and get some lights that go on or off. That's all you do. Right? Okay. So if that's right, if the computer model of the brain is right, then when you take any complex computation, if you take your ability to multiply, you can say, well, how does a human multiply? That is the kind of question psychologists study. What strategies do people use when they're trying to multiply two numbers? And you say, well, how do they do that? And one answer might be they do it by addition. But then eventually, you've got to come to primitive processes that can't be broken down any further. So the brain must have primitive processors, like these little electrical switches, right? That's what physiology is. That's what you're doing when you study the physiology of the brain. You're trying to figure out what the basic switching circuits of the brain are. That is how the computer model of the mind gets connected to the physiology of the brain. But if you think what's going on here, all you've got is a bunch of dumb processes, dumb switches flipping on and off in your brain. You've got neurons sparking into action, firing up other neurons. That's all that is going on. So one way to put Searle's point is to say, no amount of that kind of stuff could add up to the system understanding what is going on. In the case of a calculator, you can take these primitive switching circuits and say, okay, I'm going to construct it so that these lights go on when these switches are on, and you're going to get these readouts when these switches are on. You can do that as much as you like. You can make that as complex as you like. And no amount of that will stack up to the calculator understanding what it's doing. So your brain could be made of as complex an array of neurons, of physical processors, as you like, but no amount of being orchestrated like that is going to stack up to your understanding of English, to your ordinary understanding of English. How could it? Therefore, the scientific study of the mind when it's driven by the computer model, must just be a mistake. It's all off on the wrong track. Another way to put it is in terms of Nagel's thing about understanding in bats. That Nagel applied that to consciousness. But if you're thinking about trying to understand what someone's saying, if you're making a point to me and I'm saying, well, wait a minute, let me try and get what you're saying, let me try and understand that, I'm trying to imagine what's going on with you. I'm trying to get inside your head, trying to imagine what you mean by what you're saying. There is no point in trying to do that with the Chinese room. There's no point in trying to get inside this guy's head and imagine what is going on. There is no such thing. There's no head there, no relevant head there to get inside. You can't imagine what this guy means by what he's saying. Any more than you can imagine what your calculator means by what, by what it's producing. But how else could you approach the scientific study of an understanding of language? Is there some other method you could use? One answer that people sometimes give to this is, well, your brain is kind of like the chip. Your brain, is that right? Your brain is like chips. Your computer's got a chip in it, right? You're the central processor. Your brain is like your central processor. And we would never say the chip itself understands anything. So you might say, well, maybe the computer itself, maybe the whole system understands something. So maybe your brain doesn't understand English, but maybe you do, because your brain is embedded in you, in the whole system. And one way to think of it might be in terms of virtual people, that if you think of this guy's producing answers, this guy, let's suppose, might be the sweetest, most patient guy on the planet. I mean, he'd have to have quite a lot of sweetness and patience to do that stuff, right? But let's suppose that the answers coming out exhibit an irascible, short-tempered personality. They say things like, well, that was a stupid question, or I can't believe that you're supposed to be the intelligent one, and so on, right? You could get any kind of answers at all coming out there, and they might stack up to make a coherent personality. So there's some sense in which you could talk about the whole system here, the whole room, having a virtual personality that is not the same as the personality of the individual in it. Maybe you could say, well, that personality, that's what understands Chinese. What about that? Does that offer hope? Put up your hand if you think that offers hope. And if you think that does not offer hope. And if you don't understand what the question is. Oh boy, okay, right. So let me go back to where we've got to. Okay, so we're trying to give an analysis of what it is to understand English. The computer model says